So we might actually get to finish chapter 3 today. I'm excited. So what we're going to basically finish out with today is learning a little bit, and some of the folks who are in my lab section. In your lab this week, we looked at the how the linkage between the electron configuration of atoms and their size. Today we're going to get into that a little more deeply and look at the relationship between the size of the atom and its chemical reactivity. And we'll see that those atoms that are larger tend to be a lot more reactive than ones that are smaller, particularly when forming cations. And that's going to be really important when we look at metals. And today, for the first time, basically, we're also going to look at the transition metals and get a better understanding, hopefully, of why they have multiple charge states. You'll see that because of the electron configuration they have, there's a number of different electron configurations they can adopt when losing electrons that are stable. Some are more stable than others, but there's a lot of different paths to stability when losing electrons and adopting a new electron configuration. So we'll learn about that today. And also, just finishing up, we'll learn about magnetism, why some elements are magnetic and some aren't. And that will be helpful going down for further chapters. Okay, so where we left off last week, we were talking about atomic size, as I just mentioned. And one of the things that we sort of introduced, one of the new terms I introduced last week, was this term, ZF, or Z effective. Now, if you remember, when we talked about the structure of the atom, we mentioned that Z was basically the charge of the nucleus. So it was the positive charge in the nucleus. And obviously, as you add protons, this number got larger and larger and larger. What we're going to learn today is effectively, what does that mean? I mean, just because we're adding charge does not mean that it's affecting those outermost electrons exactly the same. Some increases in charge are more effective at pulling those electrons closer than others. And so we saw that as we add new shells, so the principal quantum number tells us which shell we're dealing with, 1, 2, 3. And remember, each time we add a shell, we're adding new electrons that are further away from the nucleus. So it makes perfect sense that the size of the atom is going to increase as we add new shells. Well, duh, because we're adding new electrons further away from the nucleus. Obviously, those atoms are going to get bigger. So as we go down the periodic table, as we go down a column, remember, each time we go down, that's a new shell we're adding. So if you have a periodic table, hopefully you've got one that you're going to, either you printed out one or you've made one or whatever. Write the numbers of the shell next to it, like I've done here. So we got a periodic table. And so I put a number 1 by hydrogen, and then a 2 by lithium, and a 3 by sodium. What that means is that we're adding a new shell as we go down. And so each time we add a new shell, it gets bigger, gets bigger, gets bigger. So as we go down, atoms get bigger. Okay, yeah, makes perfect sense. What may not make as much sense is as we go across the periodic table in a period, we're adding, each time we go across, and another atom adds both a proton and an electron, right? Because we're talking about neutral atoms. We're not talking about ions yet. So as we go across, sodium has 11 electrons and 11 protons too. And then we get to calcium, or sorry, magnesium. Also has an additional proton, an additional electron, and we just keep going across the periodic table, adding a proton, an electron, a proton, an electron. What may not seem apparent at first is that, yes, we're increasing the value of Z. We're increasing the positive charge of the nucleus as we go across. We're also increasing its effectiveness in pulling those electrons closer to the nucleus. And why is that? Well, it's because, remember, as we go across the periodic table, we're dealing with the same shell. It's the same principal quantum number as we go all the way across. When we're in the third period, as we go across, every one of those atoms has electrons added to the third shell. And all those electrons are basically pretty much a little bit more or less the same distance from the nucleus. And so since they're the same distance from the nucleus, and we're adding more and more and more positive charge, it's more effective at pulling those electrons closer to it. So by the time we get all the way across the periodic table, and remember, what kind of elements do we end up with when we get to the end of a period in the periodic table? What kind of element is that?
A noble gas?
Yeah, exactly. We get to a noble gas. And the noble gas, as we'll look at their relative sizes, is the smallest atom in the entire row. And why is that? It's because all of those electrons in its shell are now complete. It's got a complete shell, and it has the most protons in the whole row in its nucleus. And so it's pulling those electrons closer to the nucleus than any of the other atoms in the entire row. And so it's the smallest. So for these main group elements, and remember, the main group elements do not include the transition metals. Atomic size increases as you go down, and it decreases as you go across. And that is a general rule that we will see holds up across the periodic table. Let me give you an example of sort of what that looks like. So here are our main group elements. And you can see that especially it's really apparent in the very first group here. In the alkali metals, it's really apparent that when we add a new shell, the atom explodes in size. It gets much, much bigger because that first electron that's added in that new shell is really quite far from all the other ones. So look at the difference between lithium and hydrogen. Hydrogen has just the one S, one, right? And then when we get to lithium, we now have two S1. And that second shell is much further away from the nucleus than the first one. So lithium is a much bigger atom than hydrogen is. And as we go down the group, these elements get bigger and bigger and bigger and bigger. But look what happens as we go across. So let's look at lithium here. So lithium is 152, and these are picometers in size. And we just go across. So we're just adding a proton, adding a proton, adding a proton, adding a proton, till we get to the end of that period. And notice as we go across, those atoms get smaller and smaller and smaller and smaller until we get to neon. Neon is the smallest. It's only 71 picometers in size. So that atom is basically shrunk by half as we've gone from lithium with 3 protons to neon with 10, because those protons are pulling on those electrons more and more and more as we go across. And then once we add another electron, we go to 3s1 with sodium, boom, it explodes again. This gets much, much bigger in size. And that big increase in size is basically due to just a single electron. Because remember, there's only one electron difference between neon here and sodium. And so that single electron is much further away from the nucleus than all the others. So remember, what's the difference between, what do we call this single electron that's really far away in sodium? Remember, we have a special word to describe that single electron. What do we call it? That single electron that's in the 3s1 orbital, 3s1 subshell. What do we call that electron, that one electron that's different from all the others?
Valence electron.
Exactly. That's the valence electron. And that is the reason, basically, it's the valence electron, because it is held onto by the nucleus much, much less than all the others. So what do we call all the others? So if this 3s1 electron is the valence electron, what do we call all the others?
Core electron.
Exactly. Good job. Yeah, those are the core electrons. And we'll see that the core electrons are much closer to the nucleus than the valence electrons are. So there's basically two reasons why valence electrons are valence electrons. One, they're held onto much less tightly by the nucleus than the core electrons are. And two, once you lose it, once you lose the valence electrons, you go back to looking like a noble gas, which is what the core electrons are. The core electrons basically have a noble gas configuration. And so they stay close to the nucleus. Your valence electrons are further away. They're held on much less tightly. And we'll see that when we look at ionization. We'll learn about something called ionization energy today. Basically, how much energy does it take to pull that electron away? And we'll find out that when that electron is really, really far away and held onto much less tightly by the nucleus, not that hard to get rid of it. The ionization energy is low, really easy to pull that electron away. So any questions about sizes of the atoms and what we're looking at? Yes, Nick.
So why do the transition metals seem to stop decreasing as they go across the period?
Because they are moving their electrons in between s and p and d and f orbitals. We'll see that today. That, remember, as we go way up in the energy levels, once we get up to like about the fourth or fifth shell, the difference in energies between like D and F and P are really, really small. They become vanishingly small, so that it's much easier for electrons to move back and forth between these energy levels. And so instead of just continuously getting smaller, they basically stay about the same size as the electrons move around from different orbital to different orbital. But you'll see that basically they do, in general, have the same pattern, where they generally decrease in size. They don't always, and we'll see there's some exceptions to the rule, but basically they too get smaller as you go across the periodic table. Like, for instance, scandium here is 162, and we get all the way across, we see zinc is smaller, although zinc is a little bit bigger than copper. So in general, they also get smaller, but there's more exceptions to the rule, and we'll learn about why that is. Yeah, good question. Let me clear some of this stuff out. Oh, here we go. Okay. So, quick question here. So, hopefully you get your periodic table in front of you. Now, we've got 4 groups of elements. Now, can you group them in terms of decreasing size? In other words, put the biggest one first and the smallest one last. Okay, so find first of all, let's find calcium, magnesium, and strontium on the periodic table. Which one is going to be the biggest? Which one's going to be the smallest? What do you think?
I would think magnesium, calcium, and then strontium
So
being the
magnesium's the biggest, and then,
no, sorry, magnesium being the smallest.
oh, the smallest. Oh, okay. So strontium being the biggest.
Yes,
So strontium the biggest, and then
calcium.
calcium, and then why do you say that?
Just from I thought from going down the rows, you would get bigger because there's less. Oh, actually, never mind. If there's more electrons, then there would be more protons, which would be more pull towards the nucleus.
But are they in the same group going up and down, or are they in the same period going from side to side?
They're in the same group.
Okay, so which one? So remember, in the same group, as we go down, we're adding a new shell. So each time we add a new shell, the size of the atom increases.
Okay, then yeah, I stick with my answer.
Okay, so they're all in the same group then. And strontium is the biggest, calcium, and then magnesium. I suspect you may be correct about that. Okay, let's look at the second one. We've got potassium, gallium, and calcium. Which would be the biggest, which would be the smallest? What do we think? Are these elements in the same period or in the same group? That's the first thing you need to ask yourself.
They're in the same period.
Okay, so which one is the biggest of this particular grouping, the perioding?
Gallium.
So gallium, because it's the largest, or it's the it has more electrons or just fewer electrons?
It has the most electrons out of the three of them.
Okay, but also has the most protons too, right?
Yes.
So, but if it's in the same group as we go across, what happens to the atomic size as we go from left to right? Do they get bigger? Do they get smaller? So remember, as in a group, as we go across, those electrons are going to be in the same shell, so they're not going to be any further away from the nucleus. But at the same time, the nucleus is getting larger with more protons in it and more positive charge. So our Z effective, the positive pull of the nucleus gets bigger as we go across the periodic table. So this goes up. And as that goes up, it's more effectively pulling on those electrons. So which of these three elements, which one is furthest to the left and which one is on the right? The one furthest to the left is going to be the biggest.
So potassium.
Oh, so potassium is the furthest to the left. Okay, what's next?
Calcium. And then gallium.
And then gallium. All right, we'll check that. Okay, now we have bromine, rubidium, and krypton. Superman's favorite element. So are they going to be in the same group, the same period, or different groups in different periods?
They're in a different period and a different group.
Okay, different periods and different groups. So in that situation, which one is going to be bigger? The one that's in a different group or a different period? I guess it depends.
The one that's in the different group is going to be larger because it has, well, yeah, I
Well,
guess
if it's a larger group,
yeah,
yes.
yeah.
Exactly. So
So
which one's in the biggest group?
RB,
Rubidium. Right.
rubidium.
Rubidium is the furthest down the periodic table. And anybody who's like, if you're further down in the periodic table, you're bigger. That's just the end of that argument altogether. So rubidium should be the biggest. So then it's between bromine and krypton. Now, are they in the same period? Yes, you said rubidium was in a different period. It was in a bigger one, so it's bigger. So if bromine and krypton are now in the same period, which one is further to the left? So we have bromine and we have krypton. One of them has to be further to the left than the other one. Which one is further to the left?
A few people got the answer in the chat.
Let me have a look. Rubidium, bromine, krypton. Yes, but I would like them to explain themselves. So you're saying that bromine is further to the left. Is that what, Adriana, that's what you're saying? Bromine is, is to the left of krypton?
Yes.
Yes. Okay. So bromine and then krypton. Yeah, generally, if you got to guess, you would say that like if something's a noble gas, it's going to be the smallest because noble gases are itty bitty. And then finally, we have strontium, calcium again, and rubidium. So what would be the biggest? What would be the smallest?
Rubidium being the biggest and calcium being the smallest.
Okay, why do you say that?
Because although the atomic radius does decrease as you go down the column, rubidium is the first group compared to strontium, which is the second group, and the atomic radius would decrease as it goes across. So it would be strontium, rubidium.
So rubidium, then strontium, and then calcium.
Yeah.
Okay, let's check. I'm excited. Yep, got them all. Excellent. Yeah, so in our first situation, they're all in group 2. And so whoever is the biggest, whoever's the lowest on the list has the biggest value for N. Remember, N is just adding a new shell. And so magnesium has third shell, followed by the fourth, and then the fifth. So the bigger. The second one, potassium, calcium, and gallium, those are all in the same period. And as you go across, they get smaller. And then it would C, rubidium's the biggest because its N is equal to 5. So it's in the fifth, it has the electrons in the fifth shell. So it's automatically bigger than the other two. And then we compare krypton and bromine. Krypton is to the right of bromine, and so it's smaller. And with the last one, calcium is the lowest value of N. It's in the lowest energy level, so it's the smallest. Rubidium and strontium are in this same period, but rubidium's further to the left, so it's bigger. There you go. Excellent job. So this will give you an idea of how these sizes go. And there should be something that's a big tip off to what's going on here. So let me just show you. As we go across the periodic table, this is how the size of the elements change. And notice there is something called a periodicity here. There's a periodicity because at regular intervals, something interesting happens. So notice as we go across, we get a big jump in the size. Elements go from being small to being large. And then they get smaller and smaller and smaller. And then boom, they get large again. And then they get smaller and smaller and smaller. And then boom, they get large again. What is in common with these elements up here? What do they have in common? We have lithium, sodium, potassium, rubidium, and cesium. What do they all have in common?
They're all in the same group.
They're all in the same group. You remember which group that is?
Alkali metals.
Exactly. These are all the alkali metals. Excellent. And the alkali metals are known for being super reactive. Those are super reactive, remember? Those are the ones, if you like, take a slice of those metals and throw them into water, they will explode. They're so desperate to get rid of that one electron that is really, really far from the nucleus. So that one electron that they desperately want to get rid of, when they do, they achieve a noble gas configuration and become very, very stable. And that one electron is really far away from the nucleus, much further away from the nucleus than the others. And so they are super duper reactive for that reason. Now, let's look at the other end of the periodicity here. So let's look at these elements at the bottom. Look at all the ones that are the smallest. 1, 2, 3, 4, 5, 6. What do these elements have in common? The ones that are all the smallest.
They're all the noble gases.
They're all the noble gases. And so we see these two extremes here, right? We see the two extremes. One, here at the top, these are all the elements that are all very large. They're extremely reactive chemically. They form ions readily. And it's really easy. We'll also see that their ionization energy is extremely low. Why? Because it hardly takes any energy at all to pull this one electron away from lithium or pull this one electron away from cesium. It's very, very easy. They can't wait to get rid of it. On the other side of the scale, the smallest elements are all the most stable. So they're super duper stable. In fact, helium, neon, and argon don't form any compounds at all. Scientists have not been able to form any chemical compounds with those. On the other hand, we have been able to form compounds with xenon, and I think there's a couple of compounds possible with krypton. But argon, neon, and helium, nothing. They will not react with anything under any circumstances because they're very, very, very small. They're extremely stable. And so it's impossible to pull one of those electrons away from it or add another electron to it. So they will not form ions and they will not share electrons under any circumstances. So remember, big atoms, reactive. Small atoms, not reactive. So let's look at this ionization energy of which I've been babbling. So the ionization energy, or IE. We'll talk about this a lot, IE. That's the energy required. How much energy do you need to add to a mole of these elements? So basically remember, well, not remember, I haven't mentioned it before, but when we start talking about energy, we're going to get into thermodynamics and thermochemistry pretty soon. When we talk about energies, we always talk about energies per mole, because that's the way to so we can relate one element to another. Per mole. If it's per gram, then we have to do all sorts of calculations. But if it's per mole, then we can easily relate one element to another. So how much energy does it take? And energy we'll be measuring in joules. And we'll talk about this later when we talk about energy. This is the metric unit for energy. How much energy does it take to completely remove 1 mole of electrons from 1 mole of atoms? So if I have a mole of sodium atoms and I want to convert that to sodium ion, I need to pull that 1 electron away. And so I'm going to need to add some energy to do that. And if I don't need to add very much energy, this reaction in forming an ion is much more likely to happen. If I need to add a ton of energy to pull that electron away, then that reaction is probably not going to happen. So atoms with a low ionization energy, like as I mentioned before, they give away that electron easily. They tend to form cations. And elements that tend to form cations are what kind of elements? Remember, there's 3 different sort of groups of elements on the periodic table. Which ones tend to form cations easily or more easily? Aaron, that's right, metals. We got metals, and we got nonmetals, and we got metalloids, which are kind of in the middle. So atoms that give away that electron easily and form cations are going to be metals. Atoms with a really high ionization energy don't tend to become cations. They do not give away their electrons easily. In fact, what they tend to do more is steal electrons away from other elements. They tend to form anions. What elements are those? The elements that tend to form anions. Yeah, right. That's one group. Yep, halogens, definitely. And we'll see that halogens tend to have the highest ionization energy next to the noble gases. What group?
Is it just metals in general?
Which is it?
Is it just non-metals in general?
That's right, non-metals. Absolutely right. Those tend to be non-metals. So elements with a low ionization energy. And remember, the thing to remember when we talk about ionization energy, that's the energy required to form cations. We are stealing an electron away from those elements. So they form cations. And we know that nonmetals don't really become cations except under like extraordinary circumstances. You need to add a lot of energy to steal an electron away from a non-metal. And the halogens in particular, because they love electrons. They don't like giving them away. So ionization energy tends to go down as you go down a group. And remember, those are also the metals or atoms that are bigger. So you get bigger and bigger and bigger as you go down a group. So 2 things, they get bigger and bigger and bigger, and that electron that is really far away is not held on very tightly by the nucleus because it's so far away. And we remember, or I don't know if we remember, if I've discussed it, but when you're dealing with the attraction between charges, there's 2 things involved. One, there's the charge. So if I have a force that's holding charges together, it's based on Q1 and Q2. Q1 and Q2 being the charges, the negative charge and the positive charge. So the bigger the charges are, the more force there is holding them together. And let me move this for a sec. The further apart they are, the less that force is. This is known as Coulomb's law. Coulomb was another genius chemist with a French last name, just saying. So if you have two charges, and here we're dealing with an electron, and we're dealing with a nucleus that's positively charged, as you move them further and further away, this becomes bigger. And as the denominator gets bigger, the force holding them together gets smaller. And so as you move further and further and further away, the force, or basically the Z effective, as we've been learning, gets smaller because the distance gets smaller and smaller and smaller. On the other hand, as we're going across the periodic table, this distance stays about the same, but the Q's get bigger. Especially the size of the nucleus gets bigger. And so that positive charge gets bigger and bigger and bigger and bigger. So as you go across, the Z effective gets bigger. The force holding those electrons gets bigger as you go across. So that's why those electrons that are far away from the nucleus are easier to pull away. So let's see any questions about that? I don't know if I brought up Coulomb's law before, but it explains how these forces are either keeping a tighter hold of electrons as the number of protons increases as you go across a period. And it also explains why, as the electrons move further away, they're held onto less tightly, where it's much easier to give them away. So what I'd like to show you then is how this actually works, because this is yet another example of periodicity. Oh, okay. So here is yet another example of the periodicity. Oops, let me go back. Yeah. Okay. Damn it. Why does this keep doing this? Okay. Ah! I swear. What is going on with my computer today? Will not let me draw on. Okay, come on. Be good now. What's going on? Oh. All right, something is going on here. Let me try and get back on track. Okay, are we back? We have the screen up again. Something weird was happening with my computer. Am I back with everyone? Everyone can see the ionization energy?
Yep.
Good. Because, man, I don't know what was going on, but I was not able to show you that. Anyway, yay, I can draw again. So this is yet another periodicity, something that happens in the periodic table, something that happens with sort of this regular pattern. So we call this the first ionization energy. Anyone want to guess why we call it the first ionization energy? What might be the difference between the first ionization energy and the second ionization energy? Someone take a guess. Remember, there are no wrong answers, just wrong people with answers. What do we think? What's the first ionization energy? What does that mean?
Required in first period.
Sorry?
The energy required to remove in the first period.
No, you're close. Because there's the first ionization energy of any atom. It doesn't matter in what period it's in. Yes, right. That's right. It's the energy required to move the first electron. So it's basically the energy going from having a calcium atom and forming calcium 1+. It's that amount of energy to taking that first electron away. Now, what do you think IE2 is?
Remove the second electron.
Exactly. So this is IE1, where I'm taking the first electron away from a calcium atom and forming calcium 1+. And then my second ionization energy is the energy required to move that second electron away from calcium 1+ and forming calcium 2+. And then the third ionization energy, we're removing the third one, and the fourth would be removing the fourth one. But right now, we're just dealing with the very first. We're just taking one electron away from these atoms. And so then notice the periodicity showing a sort of pattern we may have seen before. So these are the atoms that it's the hardest to take away an electron. Helium, neon, argon, krypton, xenon, radon. What do they have in common?
The noble gas.
They're the noble gases. So it's not a surprise that that's true for two reasons. One, they're the smallest. Exactly. They're the smallest. So those electrons are being pulled toward the nucleus harder than any other atom. Their Z effective is the highest. So they are pulling on those electrons very, very tightly. So there's a lot of force holding those electrons close to the nucleus. So it takes a lot of energy to pull one away. On the other hand, look at the elements where it's the easiest to steal an electron. Lithium, sodium, potassium, rubidium, cesium. What do they have in common?
They have only one electron in the outer shell.
So which group is that? So they all have an S1 as their outermost electron, either 2 S1 or 3 or 4 or 5 or 6. They're all S1. That's their outermost electron. They only have one outermost electron. The rest are all core electrons, and they're really, really far away. So two reasons why they're the easiest. One, that electron is held on to the loosest of any of the elements. It's very far away from the nucleus, so that attraction is really, really small. And once they lose that single S electron that's far away, they look like a noble gas. So lithium goes from being very, very difficult or very, very easy to steal electron from to becoming practically impossible to steal electron from. Same with sodium. Sodium goes from being very easy to steal electron from to looking like neon, where it's practically impossible. So they go from unstable to very, very stable by taking that one electron away. So we can see that this is also periodic. Now, this is just give you an idea So these are the main group elements. Again, we're not looking at the transition metals yet. We'll look at them in a second. So we can see two patterns going on. What are the two patterns that you notice of the ionization energy as we look at as we look at the table here? What are the two things that sort of jump out at you? What do we think? There's two patterns sort of that we can
As
see.
the number of proton increase in a group in a period, the energy has to increase.
So the energy increases in what pattern? As you get larger or as you get smaller?
Smaller.
So in a period, they get smaller as you get, the amount of energy required to steal an electron gets smaller as the element gets bigger. So we can see with hydrogen, you need to add a relatively high amount of energy to get that to ionize, and then it gets smaller and smaller and smaller and smaller as you increase in size. And what's the other sort of pattern that we see? So the ionization energy goes down as in a group as the atom gets bigger. What happens though when we go across in a period? What happens? What's the second part of the pattern here? So there's just two things going on that are sort of periodic. Ionization energy decreases as you get bigger in a group. What about across? Does it get bigger or smaller? Yeah, it gets, right, Brian, it gets larger as you go from left to right. So just like atomic size, you see the same sort of pattern here. The atomic size gets smaller as you go from left to right, as the Z effective, or the pull of the nucleus, gets larger as you go from left to right. Two things happen. As the protons pull on those outermost electrons more tightly, the atom gets smaller, and the amount of energy it takes to steal those electrons gets larger because there's more force. There's more attractive force on those electrons. As the atoms get smaller, there's more attractive force on those outermost electrons. And so it takes more and more and more energy to take them. As you see, it gets bigger as you go across. Okay, does everyone see how that works? How they're sort of related to each other. As you pull those electrons closer to the nucleus, that force of attraction gets larger, and you need to add more energy to overcome it and steal that electron away. So it's all related to each other. So another quick quiz. Just have a look at your periodic table, and then which ones do you think has the highest ionization energy going to the lowest? Starting with, and then think of, are they in the same group? Are they in the same period? Or are they in different groups and periods? So here we have krypton, helium, and argon. I suspect those are in the same group. They sound kind of familiar. So which one would have the highest ionization energy? Which one would be the most difficult to steal an electron from? And then which one would be the easiest?
Helium,
Mm-hmm.
the hardest one.
Yep.
Then argon. And then krypton.
And why do you say that?
Because the size is increasing along the period.
Exactly. Yeah, krypton's the biggest. And since krypton's the biggest, remember the attraction for those electrons far away and the nucleus gets smaller as the atom gets bigger. And so that attractive force gets smaller and smaller and smaller as the atom gets bigger. Krypton's the biggest, so it should be the easiest of those three to steal an electron from, although still pretty difficult because it's a noble gas. So next, we have antimony, tellurium, and tin. Sb, Te, and Sn. I suspect those are in the same group. I suspect those are in the same period.
I can't even find SB. Where is SB?
Let me look. Sb is SB is number 51. Antimony is 51. Just below arsenic. Tellurium's in group 6.
52, 51, 50.
Yep, you got them. So what order? Which one would have the highest ionization energy? Which one would have the lowest?
Tellurium, the highest, and then antimony, right?
Mhm.
And then tin.
So Te has the highest,
Yes.
followed
That's
by so tellurium, followed by antimony, followed by tin. Okay. Potassium, calcium, rubidium. You have to type faster, Ferris. You got it. Let's do this last one. Potassium, calcium, rubidium. Potassium's 19, calcium's 20, and rubidium is 37.
How to compare calcium and rubidium?
Well, remember when we add, so rubidium is larger than either. So rubidium is the largest. So it has a different shell, has a higher energy level, a higher principal energy level, or a higher shell. So what do you think? So as we get bigger going down, what effect does that have on the ionization energy?
Oh, I see.
Yeah.
The bigger one is like lower energy.
Lower ionization energy. Yeah, that should be the smallest.
Yeah. So rubidium, and then potassium and calcium.
So which one would be, so highest would be calcium would be the highest, and then potassium,
Mm-mm.
and then
Potassium.
rubidium. Okay, so let's have a look. I think you may be right. So, yeah, the first three, all noble gases. As you get bigger, the ionization energy decreases. So, yeah, the smallest one would be the most difficult to steal. Tellurium, antimony, and tin, all in the same period. And as you go across, it gets more difficult to remove an electron. So the size, the smallest, tin would be the biggest, and so the most difficult to steal an electron. And then, yeah, calcium, potassium, rubidium. Rubidium is the biggest. So it's the easiest one because it has a whole new shell. So much easier to steal that electron. And then calcium is slightly further is slightly bigger than potassium. And then finally, we had xenon, iodine, and cesium. Xenon, the toughest to steal because it is a noble gas. Iodine is a halogen, so also quite difficult to steal that. And then cesium is the biggest, and it's an alkali metal, so quite easy to steal an electron from cesium. Okay, so now we're going to look and see how we can identify which are the valence electrons and which are the core electrons, just based on how easy it is to steal that electron. What are the ionization energies to steal an electron? And so we've already noticed that for, let's go back. For the first group, for the alkali metals, it's pretty easy to steal that first electron, right? As we go across, they all have one the valence electron. The rest are all core electrons, and it's really easy to take it. Very, very low energy required to take that electron. But what happens when it's time to steal the next one? And that is how we can see how many valence electrons and how many core electrons an element has. Now this is beryllium. Let me go back. Beryllium. How many electrons does beryllium have? What's the atomic number of beryllium? It's one of the small ones. Four, right, Paris, that's 4. So it has 1s2, 2s2. That is the electron configuration for beryllium. So it just has those 4 electrons, and that's it. So this is the amount of energy required to go from neutral beryllium atom to beryllium plus and an electron. This amount of energy right here. Very little. So this is like, I think or megajoules per mole, just whatever. It'll give you an idea of how many joules it's required to do. Not very much. So small amount of energy. The second energy, remember IE2, ionization energy 2, is the amount of energy required to steal the second electron, not the first and the second, just the second one after you've taken the first one. So it took this much energy to steal the first one. Now this second one is Be plus, and we're taking another electron, we're adding energy, and we're stealing another electron to form Be2 plus and take another electron. That's IE2. And notice that's not very much either. It's more than the first one, but not that much. Now, this is the third ionization energy. So this is the amount of energy required to take Be2 plus, add some energy, and form Be plus 3 and taking an electron. And notice how much it jumps in a huge way. It goes from 0.9 to 1.8 to 15. So there's a huge jump in the amount of energy required to pull another electron away. And why is that? Well, because the first electron was in the 2s. The second electron was also in the 2s. But where's the third one? In the 1s. So there's 2 things happening. One, it becomes more difficult to steal electrons as we go along, because remember, now we have more protons than electrons. When we have a positive ion, that automatically means there's now more protons than electrons. And so naturally, it's going to be more difficult to steal another electron because this attraction becomes even more. The pull that the protons have are even greater now. Second thing that's going on is that we went from pulling away valence electrons that are far from the nucleus to core electrons that are really close. And so those core electrons are held onto very tightly by the nucleus because they're really, really close. And we know that electrons that are close are going to be pulled on very tightly. That attractive force is going to be really high. And so we can see just by the amount of energy required to get those electrons that beryllium has 1, 2 valence electrons that are relatively easy to take. And then the next one is a core electron. So we can easily see that beryllium has 2 valence electrons and 2 core electrons, just like we would predict from its electron configuration. Any questions about the sort of the logic of how this works? The electrons that are relatively easy to steal, those are valence electrons. The ones that are really tough, those are core electrons. So we can basically measure it just by adding energy and seeing how tough it is to ionize these things. And wherever we see a big jump, that means we've entered core electron territory. Let's see if you'll notice there's also another pattern. There's a periodicity here as well. So let's have a look at a couple of different elements. So we'll go from lithium through to sodium, and you'll see that there's a pattern here. So lithium, here's lithium here. And we look at the energy required to steal 1 electron. Not very much. How much does it take to steal a second electron? Over 10 times more. You see that big jump means that this is a valence electron and this isn't, because of that huge jump in the amount of energy required to take that second one. That means that these two are core electrons and this one is a valence. So lithium only has 3 electrons. 2 of them are cores and 1 of them is valence. Now, as we go down, look and see, difficult to talk. Look and see what happens. Let's go down to carbon, for instance. So we're trying to ionize carbon, meaning we're taking electrons away from carbon. So first one, not that hard. Second one, harder, yes, but still. Third one, about twice as much. The fourth one, about 50% higher. Fifth one is now 5 times higher than that last one. So you notice that it jumps in a huge way. So the first one, relatively straightforward. Second one, twice as hard. Third one, twice as hard again. Fourth one, about 50% increase. But then when we hit the fifth one, there's a 500% increase in the amount of energy. What does that tell us? It tells us that carbon has 1, 2, 3, 4 valence electrons. And if we look at the electrons carbon has, 1s2, 2s2, 2p2. This is a core electron. These are valence electrons. So, and we can see it just based on this pattern, how many core electrons it has. Now, based on this, look at sodium. How many core electrons would you suspect sodium has? Look at the pattern. Look at the increase in ionization energy. Where's the jump? Yes, Ferris, that is true. That's a 10-fold increase from IE1 to IE2. That means if you see a 10-fold increase, that means you have entered core electrons. Now compare that. So it has 1. So this one's easy, much more difficult. Compare that to fluorine. Fluorine is interesting. Now fluorine is going to be difficult to ionize anyway because it's hard to steal electrons away from fluorine. But look and see when it becomes very difficult. So we start, notice that already it's much harder to steal an electron away from fluorine than it is from sodium. Well, that makes sense. Sodium is an alkali metal with 1 electron really far away. It's easy to take. Now, we go from fluorine. The first one is difficult. Second one, we see an increase of about 100%, increase of about 100%, increase of about 50%, increase of about 30% maybe, another increase of about 30%, another increase of about maybe 5%, and then look at that. Then it jumps. Then we get about a 6-fold increase. What happened? So it went steadily got more and more difficult, but it wasn't until we got to the 8th electron that we saw a big, like 500-600% jump. Why? Because fluorine has 1, 2, 3, 4, 5, 6, 7 valence electrons until you get to the core. Because when we look at fluorine, it's 1s2, 2s2, 2p5. So these are the 7 valence electrons that fluorine has, and these 2 are the core. So that's how we can sort of identify which elements are core, which elements are valence, just based on how hard it is to take them away from the nucleus. Now you have to look at each one separately, because we can see all the way across it's difficult to take electrons away from fluorine. We would expect that. But it becomes really difficult to take electrons away from fluorine only when we get to like the very last one. We can take 7 away relatively more easily than the 8th one. There's a big jump when we get to the 8th one. So that tells us there's something similar about the first 7 and something different about the last one. And the difference is the first 7 are valence electrons and the last one is a core. So any questions about that one? Just have a couple minutes left. I want to see how far we can get. We will. I mean, we're not going to rush. We'll finish this next week. But I just want to just show a couple more things. So, yeah, why don't we just finish here? This will give you an idea of what I'm talking about. So this are the ionization energies of a period 3 element. So in the 3rd row, and these are its ionization energies. This is the first one, and then we go across until we get to the 6th one. Now, what element is this? First one to answer doesn't have to take the test on Tuesday. Oh, you got in there too early, Ryan. Sorry. That's right. So when does it increase? So we see about 90% increase, or 90% increase, or 90% increase, 50% increase, 350% increase. So it's at that point where it jumps. And so it has 1, 2, 3, 4, 5 valence electrons. And who has 5 valence electrons in the third period? That would be phosphorus. And we can see which ones are the valence electrons based on its configuration. So 1s2, 2s2, 2p6. So those are in the first n equals 1, n equals 2, n equals 3. So the furthest energy level, the third shell, it's in period 3. It's got to have 3 shells, right? So 1, 2, then finally when we get to the third shell, it has 3s2, 3p3. 2 plus 3 is 5. 5 valence electrons. Okay? Good job. So I'm going to end up there, leave a couple of minutes for questions. I mentioned at the beginning of class, maybe some of you missed it, that I have posted answer key for recitation 1 and 2. I haven't done for 3 and 4 yet because some people still are sending it in. But any questions you have about recitations or the test or anything, this afternoon's recitation section will be a review. And so if you have time, come by and we will review any question you like this afternoon, and we'll stay for as long as it takes. Okay? Any other questions about either what we've learned today or the test on Tuesday? And obviously you can send a text or an email, not a text, but an email to Canvas or directly to me. I answer those pretty quickly. Yes, Nick.
I was just wondering, since we don't have the answer key yet, is it okay if like today in recitation we go over some that I might think I have wrong?
That's the point. That's
Okay.
exactly the point. Yes. Yeah, that's the whole point of doing it. Yeah, you don't want to review the ones you know you've got right. That's the point of that. Yeah, I know this. I would like to learn it some more. No, we want to go over the stuff that we don't know. Oh, Aaron, yes, the last question of the test is exceptionally hard. It's optional hard. Damn it. I'm hoping it's both optional and exceptionally hard. Yeah, I try and make the bonus question. It'll be worth like 5, generally worth 5. If the test is 100, I make it worth 5. On the final, which is worth 200, I'll make it worth 10. Yeah, I try and make it a difficult question that you have to answer completely correctly to get the value. And it's optional. You don't have to do it. But I would suggest, why not? You have literally nothing to lose, right? If you get it wrong, who cares? Will it be doable with the content? Yes. Hopefully, yeah. Yeah, I'm not going to make you do a research paper during test time. That even I'm not that cruel. Although that's a really good idea, Aaron. Maybe I should do that. Remember, this was Aaron's idea, everyone, to make you do a research paper during a test. So if you know where he lives, I'll send out his address.
But we will have like probably questions from recitation that are kind of on the
They'll be
same.
very similar. Yeah, they'll be very similar to the recitation questions. Yeah, I mean, they're obviously not going to be exactly the same, but they'll be fairly similar in scope and in tenor. All right. Anybody else have anything before we call it a morning? I'll see you at 1:10. Okay. All right. Have a good morning, everybody. Relax. It's going to be okay. We'll talk to you soon.